So what still remains is we have to solve the generalized network flow problem in Excel, the example with recycling problem. So how can we solve it? Well, we have to use one of the formats that we used for the first problem in chapter 5 for the transshipment problem. And if you remember, I showed you two variants. One was with the standard linear programming model where we enter all the coefficients for all variables. So this was the problem of putting 1 and -1 coefficients for the right variables. And the other was with using the sum-if functions. Now, if you want to use the first variant, it's quite straightforward to put this model. All that changes is that instead of having -1 and 1 coefficients, notice here for x15 you have -1 when it is the outflow, but you have not +1, you have 0.9 plus 0.9 when it is an inflow, right? And the same thing for all variables. So all that changes is you don't have -1 plus 1, you have -1 and plus yield. When they are inflow variables, they are not +1, they have plus yield value, which is usually fractional, less than or 1 in this example. But in other examples, when the yield is higher than 1, it would be also higher than 1. So the first model, first type of the model, I think you should be easy for you to understand. The second variant of the model I'm going to present here now. So what do we have to put? Well, first of all, instead of just having variables flow, I have to say, right, the variables are flow out of node I. So I will define flow out variable. Now I will also put flow in, which will be calculated as yield times flow out, right? So we'll have like two versions of variable. One is before multiplying by the yield, the other is after multiplying by yield, right? We also need from to variables, and now we need cost, but we also need, or let's put yield first, and then let's put cost second, right? So what we will have is we'll have a number of variables. How many variables are here, right? There is 4 nodes connected to each of them to 2, so that makes 4 times 2, that's 8 variables. And then there is another 2 times 3, that's 6 variables. So in total we will have 8 plus 6, 14 variables. So I'll have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 variables. Let me mark them, right? And then let's say from where to where are they? Well, they are from node 1 to 5, from node 1 to 6, from node 2 to 5, 2 to 6, 3 to 5, 3 to 6, 4 to 5, 4 to 6. And then this was the first stage, right? Well, stage 1 to stage 2, and then stage 2 to stage 3 is 5, 7, 5, 8, 5, 9, and then 6, 7, 6, 8, 6, 9, right? So this is from 2. Now I have to fill out the yield and cost. And now that I have yields and costs, I can do some calculations. First of all, I can compute the flow in value based on the yield, right? If there is a float value here, what flows in, as I said, right, flow into a node here in the definition is the yield times the flow out, xij. So I can say here this is equal to yield times flow out, right? And this is of course our formula. It's not a finished formula for a constraint, but it's a value I will use later on in the constraints. So let's test it. Let's see. If I have 10 units flowing out from node 1 to 5, I will have 9 units flowing into node 5 when they arrive, right? Also, we can now put the total cost with the cost. So I can say total cost is, and I can put here, this is a standard sum product of costs, and now you be careful, it's a cost for units that are flowing out, not units that are flowing in, right? There are no yields here. 13 times x15, this is the flow out. So so the cost is 130, is that correct? 10 tons are moving from node 1 to 5, and it costs $13 for each. The cost is 130. This is also the function, so I define it like this. So that's the first part. Now we have to put the constraints, right? We have the objective, we have the decision variables, we have some additional formulas, but these are not yet for the constraints. We have to put constraints for each node. So again, we will have node, and we have 1, 2, and I can do the same thing as before. I can drag it down to make it 9, right? I have 9 nodes, and I can say I need the inflow minus outflow, right? In minus out, the net flow. I need the net flow calculation here. So and then I will have to say, well, this net flow has to be compared to the right hand side, or the BI value, which I know what they will be. They are minus 70. Let's enter the easy things first. Minus 50, minus 30, minus 40. That's the supplies. Then nodes 5 and 6 have no supply, no demand. I have to put zeros, and then 60, 40, and 50 are demands. Notice I put here zeros, although this is optional. If you skip the 0 here and skip the 0 here, it will mean this is a transshipment node, no supply, no demand. So what is the inflow minus outflow? Again, we have to use the sum if functions. And now the difference is, there's only one difference from what we did before, right? Before we were taking, for the inflow, those variables that have a right index in the to column, and for outflow the right index in the from column. However, now we will in one of the sum if we'll take flow outs, and in another sum if we'll take flow ins, because when they are flow out of nodes, right, when they flow out they are regular units. When they flow in, they are multiplied by yield, so I want to add those values that are flow outs multiplied by yield. That's why I computed them here. So now let's write those. The inflow, as we said, in the inflow, when it flows into node 5, there is a loss. We multiply by yield. So for the inflow, it will be sum if, which range do we check in this? If it is an inflow, the to index, so this range, press F4 to fix the range, must be equal. Criteria is the node number. So I'm looking for node 1. Again, it is not going to work. This is not going to return anything because there is no node 1 here, but remember I'm writing a general formula to copy paste here. So I3 is where I'm looking for the node number. It says node number 1. I'm looking for node number 1 here, and then I will be adding all the flow in values, which are these, right, multiplied by yields. And I press F4 here to fix this formula. So this is the flow in general formula, minus flow out is another sum if, where I take the range, I check in the from index, right? I'm looking in the from index, press F4 to fix the range, comma, I'm looking for in this range for node number 1, comma, and I will be adding the flow out, right? Variables, the variables themselves without multiplying them by yields. Again, press F4 so that when I copy this formula, it is all correct. So now you'll see, all right, when we're moving 10 units out of node 1 to node 5, we are having a net flow in node 1 minus 10, because we just took 10 units and delivered nothing, right? And then this is okay because we have maximum 70. And okay, so this is a formula. Let me copy it down here, and you'll see that this formula also, when I edit it, when I press F2 to edit it, it takes the appropriate ranges. So I think I fixed, right? It is taking I4, which is now node 2, and it is looking in those ranges from 2 for this index 2, and then adding appropriate flow out or flow in variables. The ranges look okay. And the interesting part is you notice that the net flow in node 5 is 9. Is that correct? Yes, because we sent 10 units from node 1 to 5, and there is a yield, so what arrives in node 5 is 9 units, and we can see net flow correctly calculated, which is now infeasible, right? Because here we should have 0, so these 9 units should be taken further to the demand nodes. So let's solve this now. This is ready for solving, right? And as I said at the beginning, I will assume greater than or equal constraints for inflow minus outflow, greater than or equal right hand sides. But we'll see if it is feasible, and if it is feasible, we'll accept the solution. If not, we'll resolve it with less than or equal. So let's see how do we define this model. We want to take the total cost and minimize it. Take it subject, changing variables. Now be careful here. just change the flow out variables. These are not variables, even though they look like. These are actually functions that are calculated based on variables. If you select also this column, it will overwrite your function here, which is yield times flow out, right? So this is like an intermediary function used later by the inflow outflow calculation, right? The variables are still this column only. And then add the constraints, and the constraints are as before. Inflow minus outflow will be, we said, greater than or equal to the right hand sides, add, and then just flow out is greater than or equal to 0. Okay, so now we have this formula. We uncheck this box, we select simplex LP as the solving method, and hopefully everything works. I'll click solve. The solver found a solution. All constraints and optimality conditions are satisfied. So it seems the model is feasible with greater than or equal sign. We found a solution. We could ask for answer and sensitivity reports and so on. And but I'm not going to do this here. Let's check the solution. We can see the balances. So I can see that I am taking exactly as available for the first 3 products, 70, 50 and 30 tons, but I'm not using all 40 tons of the 4th material, the cardboards. I'm only using 35 point something. Okay, there is nothing left in the transshipment nodes, and that's correct, right? In this recycling process 1, 2 intermediate nodes, nothing is left, and what is delivered to the demand nodes is exactly as demanded. So we satisfied all the demands without exceeding all the supplies. So our assumption was correct, and you can see the total cost is this, and you can actually see how many units flow were on those connections. So we can, for example, identify that it's 43 tons, just over 43 tons of newspaper going to process 1, and 26 point something going to process 2, newspaper to process 1, newspaper to process 2. Then, for example, all 50 tons of mixed paper go to process 1 to node 5, it's here, and nothing goes to process 2. All 30 go to, of 30 of white office paper go to process 5 also, and so on. We can try to detect what happens, right, in the remaining parts, how much we're moving then from process 1 and 2 to those products to produce them finally, right? All the yields have been accounted for, and we have the total cost of processing minimized, and it is equal to this. So this is the solution, tells us what to do, and this is the optimal objective function value, which tells us the value of this solution, and we know this should be now the best possible.